Let us now look in detail the components of a convolutional neural network. As already discussed, the CNN has two components. The first component is responsible for feature learning or feature extraction, and the second part is associated with classification. And as we can see in feature extraction, we have the convolutional operation, the activation function, and a pooling layer or a pooling operation. Now, convolution is one of the main building blocks of a CNN. It is this convolutional operation that maps a local receptive field into a neuron in a hidden layer. In the case of a CNN, this convolution operation is performed with the help of what is called as a kernel or a filter. And it is this kernel or filter that produces a feature map. Or in another terms, or put it in another way, the convolution is performed on the data with the use of the filters or kernels to then produce a feature map. For example, suppose my local receptive field is what is represented here in green, and imagine this is my kernel or a filter. So how this mapping happens is this 3 into -1 plus 0 into 0 plus 1 into 1 plus 2 into -2 plus 6 into 0 plus 2 into 2 plus 2 into -1 plus 4 into 0 plus 1 into 1. And when you perform that operation, you get a single value which is -3. So we execute a convolution by then sliding this filter over the entire input. Let us consider that I have an image, and this is the image which is a 5x5 image, and I'm performing a convolution operation with the help of a 3x3 filter, or we also call it as kernel. And my kernel is 1 0 1 0 1 0 1 0 1. So this kernel has to be mapped into my image, or we are performing a convolutional operation. And for this, since it is a 3x3 kernel, I will choose a 3x3 window on my image and perform my convolution operation. So that would be 1, that is this 1 into 1 plus this 1 into 0 plus 1 into 1 plus 0 into 0 plus 1 into 1 plus 1 into 0 plus 0 into 1 plus 0 into 0 plus 1 into 1. And this would give us the answer 4. So that now I have 4 after my first kernel operation on my first local receptive field. And as I have mentioned, we execute a convolution by sliding the filter over the image. So my next will be this particular local receptive field, and I do the same process. So it would be 1 into 1 plus 1 into 0 plus 0 into 1 plus 1 into 0 plus 1 into 1 plus 1 into 0 plus 0 into 1 plus 1 into 0 plus finally 1 into 1. And this would give me a value 3. So I have my 3 here. And finally, you do the same process also at this new local receptive field, and this would again give me an answer. So if you do that, you get an answer or value of 4. Now the next local receptive field I will be choosing is this one. And as I continue this process, I would get a 3 cross 3 result with values 2, 4, 3 and the remaining values as 2, 3, 4. Now from this example, I can say that if I have an image which is of size n cross n, and if I have a filter of shape f cross f, then this output image that is created using the convolutional operation will be of the shape or will be of the size n minus f plus 1 cross n minus f plus 1. Now going back to this example we have considered, in this example I have a 5 cross 5 image. That means n is equal to 5. 5 minus the filter I have used is 3 cross 3, that is minus 3 plus 1 cross 5 minus 3 plus 1. So 5 minus 3 is 2, 2 plus 1 it is 3. So that is how I get a 3 cross 3 output like this. I also wanted to introduce a term which is called as stride. Stride is the size of the step the convolutional filter move each time. And usually we keep the stride size to be 1. For example, in the previous example we have considered, we had a 5 cross 5 image and 3 cross 3 kernel. And the first local receptive field I chose was here. And since I have used a stride is equal to 1, that is why in the second local receptive field I was chosen was 1 step. So that is, it was this one, right? And similarly, the third one was again 1 step forward, and so this is my local receptive field. So stride is the size of the step the convolutional filter moves each time. So this is the same that happens from left to right as well as from top to bottom. So if you have a stride of 1, now once up to this portion is moved, what happens is that the next local receptive field that will be chosen is 1 step ahead. So that is, it would be something like this, right? And then the next would be here, and then it would be here, right? And after that, 1 more step below, and then it would be this particular local receptive field. So stride is again a common terminology when we deal with CNN. It is nothing but the size of the step the convolutional filters move each time. So a convolutional operator is one of the fundamental building block of a convolutional neural network. In this example, I have used a kernel or a filter which is called as a Sobel filter. And Sobel filter or kernel is a filter that helps us to detect vertical edges. So using this filter, we can detect vertical edges in our image. So the question comes, do we actually have to provide these kernels or these filters in order to train our neural network? That is, should we handpick these 9 values present in this particular filter while we are working with a convolutional neural network? The answer is no. So this is where we use this power of deep learning, wherein which you don't need to have a computer vision researcher handpick these 9 numbers. But instead, what we do is we treat these 9 numbers, which is a part of our filter, as a parameter, which you can then learn using a backpropagation. So the goal is to learn this 9 parameter so that when you take the image or when you take a 6x6 image and convolve it with, say, a 3x3 filter, then this 3x3 filter will give you a good edge detection from that image. So this is what we mean when you say when you are training a convolutional neural network. So we are not handpicking these values, these 9 values in our kernel or the filter, but rather we treat it as parameters or weights of our neural network, and we let our neural network learn that for itself during the process of backpropagation. So this idea of treating these 9 numbers in your kernel as a parameter to be learned has been one of the most powerful ideas in computer vision. Now, there are two downsides of the convolutional operation that we just discussed. The first downside is, suppose that you consider an n cross n image and an f cross f filter. We said that the resultant image size would be now n minus f plus 1 cross, of course, n minus f plus 1. So let us imagine that you have a 5 cross 5 image and a kernel of size 3 cross 3. Kernel of size 3 cross 3. So after the first convolutional operation, your image shrinks. So your image shrinks to say 3 cross 3. Now again, when you apply the same f cross f filter, which is the 3 cross 3 filter, your image further shrinks to n minus f plus 1, which is 3 minus 3 plus 1, which is 1. So you get a 1 cross 1 image, or you just have a single pixel that you have, a single pixel, or this is a 1 cross 1 image, right? Or what I wanted to say is that when you apply the convolutional operator, your image starts to shrink, and you can apply convolutional operation only a few times before your image really becomes very, very small, right? So that is one drawback of using a convolutional operation. Another downside of a convolutional operation is that the pixels at the corners or at the edge of an image is used only in one of the output, whereas if you take a pixel in the middle, there are a lot of 3 by 3 regions that overlaps that pixel. For example, if you take this particular pixel which is at the corner, you could see that it is just in one operation this pixel value is being used. Whereas if you consider a pixel somewhere in the middle, that is, suppose you consider this pixel, in that case this pixel becomes a part of so many overlaps. So it is used here, then it is used here, right? It is also used here, and it is also used here. It is also used in this overlap, right? And it is also used in this overlap. So clearly we can see that the pixels at the corners or at the edges of an image is used only once in the output, whereas the ones that is near to the center becomes a part of more than one overlap. So the pixels on the corners or the edges are used much less in the output. So that means you are literally throwing away a lot of information near the edges of the image. Now this is where the concept called as padding comes into play. So the padding helps us to overcome the two drawbacks of the convolutional operations that we have just discussed. Let us now discuss about padding. So as I have mentioned, padding is a method to overcome the two drawbacks of a convolutional operation. That is, the first drawback was the image shrinking to a very smaller size at a very fast rate, and the second drawback is the pixels in the corner of the images not being utilized very well. So let us first see an example with a 6x6 image which is convolved by a 3x3 filter. Then the resultant image would be n minus f plus 1 cross n minus f plus 1, which is 6 minus 3 plus 1 into 6 minus 3 plus 1, which is equal to 4 cross 4. Right? Now, padding is a method by which we add an extra border around our image. So, suppose that I am adding one layer around my image. So I will have my new image as something like this. Which means my new image with an additional one border around the edges will be of size 8 cross 8. Now to that, when I apply a 3 cross 3 filter, my resultant image would be n minus f plus 1, which is equal to 8 minus 3 plus 1, which is equal to 6 cross 6. So here clearly we can see that the rate at which my image shrinks is now less, right? So in my initial case, when there was no padding, then my image shrink to 4 cross 4 in the very first convolution operation. Whereas after adding a filter after adding a padding of one layer, now my image shrinks to only 6 cross 6 after my first convolution operation. We could also clearly see from this example that after padding, this particular image, this particular pixel, which was originally the corner pixel, is no longer the corner pixel, which means it can be now part of more than one output mapping. Right? So that is how the two drawbacks of convolutional operation is overcome by doing a padding operation. Now by convention, we pad by 0. So all these positions, pixel values will be 0. And P is represented as the padding amount. So in this case, we have used P is equal to 1. That is why we have added one layer or one border for our original image, because my padding amount is equal to 1. So if my padding amount is equal to 1, that means I am adding an extra border to my image. Now in that case, what happens is that my output image after a convolution operation, so if I have an image of size n cross n and I have a filter of size f cross f, and I'm also using a padding on my input image. In that case, after this convolutional operation, my size of the output would be n minus 2p minus f plus 1. So n plus 2p minus f plus 1 cross, of course, n plus 2p minus f plus 1. For example, in the image example we have considered, n, which is the size of the image, is 6. So 6 plus 2 into the padding size was 1, 2 into 1, minus f was 3 plus 1. So that is 6 plus 2 minus 3 plus 1, that is 8 minus 3 plus 1, which is equal to 5 plus 1, which is 6. So we get a 6 cross 6 output from this convolution, and if you remember, see, this is exactly what we got. So my formula becomes a bit changed as n plus 2p minus f plus 1 if I am considering my padding operation. In terms of the question of how much to pad, it turns out that there are two common choices for padding values. So one is the valid convolutions and the second one is the same convolutions. Valid convolution means no padding, which means that if I will have an n cross n image that would be convolved by an f cross f filter, and it would give me a new image of size n minus f plus 1 cross n minus f plus 1. Whereas in the same convolution, it means that when you pad, the output size is the same as the input size. That is, of course, when you are using padding, so if you have valid convolution, that means you are not using padding. In same convolution, you are using padding. That means my output would be n plus 2p minus f plus 1 cross n plus 2p minus f plus 1. And so this output that is n plus 2p minus f plus 1, should be equal to my input. So in that case, these cancel out, and what you get is 2p is equal to f minus 1, or p is equal to f minus 1 by 2. So, for example, if I have a filter of 3 cross 3, then we had a padding of P is equal to F, which is filter minus 1 by 2, which is 2 by 2 equal to 1. So basically, in the example where we have used for padding, that is this particular example we were doing is an example of same convolution, because in this case I have chose my padding as padding value to be P is equal to F minus 1 by 2, which is 3 minus 1 by 2, which is equal to 1. That is why I just had one border of padding given to this image. So we have already talked about stride. So stride is the size of the step. It is the size of the step the convolutional filters move each time. So stride convolution is also another piece in the basic building block of a convolution as used in a CNN. Now, suppose that I have a 7 cross 7 image. It's a 7 cross 7 image, and I am using a 3 cross 3 filter, and I'm saying I'm using a stride of 2. So that means my first layer would be this, right? So since I have a stride of 2, the size of my step would be 2. That means literally I would jump to this position. So my next operation will be done on this set of pixels, and then jumps to here, and my next operation will be done on this pixel. And similarly, when you consider the downward motion, downward transfer, my next stride would be from here to here, because I have now jumped 2 positions. So this would in turn give me a output size of a 3 cross 3 image. So again, stride plays an important role in determining the size of the output image. So if you have an n cross n image and it's convolved with a f cross f filter, and we are using a padding of P and a stride of S, in that case my final output would be the floor, that is, I'll consider the lowest value I will round to the lowest digit when I have a decimal value. So it is n plus 2p minus f plus 1 divided by s cross again n plus 2p minus f by s plus 1. So this 1 does not have a remainder s, it is just n plus 2p minus f by s plus 1 cross n plus 2p minus f by s plus 1. So in case during this process we get a decimal value, we round it to the lowest value. The next important part of a convolutional neural network is the pooling operation. The function of pooling is to continuously reduce the dimensionality, which in turn reduce the number of parameters and the computations in the network. It is this pooling operation that shortens the training time and controls overfitting. As I have mentioned, there are different types of pooling, but the most common type of pooling is called as max pooling. Now, in this example, you could see that in order to do a pooling operation, I have used a window size of 2 cross 2 and a stride of 2. So obviously this would be my first window, which is shown in pink color, and since I have chosen a stride of 2, it will jump to this particular location. And that is why I have this portion selected as my next 2 cross 2 window. So if I am having a maximum pooling, of course in the first window I have selected the maximum value is 6. In the second window it is 8. In the third one it is 3. And fourth one it is 4. So similar to max pooling, we also have average pooling. So here in this particular example, I have an average pooling. Again, I have taken a window size of 2 cross 2 and a stride of 2. So in that case, my green colors represents one particular window, and as you can see, what we have done is we have found the average of these 4 values in this green window, and that is 36. Similarly, if we find the average of the other 4 values in our next window, and its average is 80. So pooling is a very important functionality of a CNN architecture, as it is the one that is responsible for reducing the dimensions, thereby reducing the number of parameters, thereby reducing the training time and controlling overfitting. So as we have already discussed, our components of CNN is broadly divided into feature learning or feature extraction and then the classification. So all the concepts that we have mentioned, like the convolution, the ReLU operation, the pooling, the functionality of stride, the functionality of padding, all those are applied in this feature learning or feature extraction part. And after the convolution and pooling layers, we have our classification part, which as you can see has a fully connected layer. And this fully connected layer can only accept one-dimensional data. So whatever 3D data we have at the end of this feature extraction is flattened in order to convert into a one-dimensional vector, which is then connected to a fully connected neural network. So this particular portion of your CNN is actually the same as your traditional neural network. Now, training in a CNN works in the same way as a regular neural network using backpropagation and gradient descent. But however, in the case of a CNN, it is a bit more mathematically complex process because of these convolutional operations. Convolutions over volume. So as we know, the images basically are of two types, a grayscale image and a color image. So till now we have looked into the operations or the components of CNN, which is from a perspective of a grayscale or binary image. Now, most of the cases, the image that we have to deal with is a RGB image or an image with a depth of 3. So in that case, all the operations are the same. The only thing is that it is now has to be done to the red channel, green channel as well as the blue channel, and then it has to be merged as an output. For example, here I have an RGB image. The values of R is represented here. The values in the green are represented here, and the values of the blue channel are represented here. Now these three channels has to be now separately convolved with the filters. So I have a filter, a 3x3 filter for my red component, another filter for the green component, and another filter for the blue component in my color image. Now that is then processed separately. So we do a convolution operation on the red component separately and we find its result. Similarly, we do it separately for the green component and blue component. After that, we combine this result or we add these values. So you could see 7 plus 5 plus 7, that is 19. That is how I get my 19. Similarly, 5 plus 3 plus 5, that is how I get the 13. And similarly with rest of the value. So in short, working with a grayscale image and working with an RGB is not much of a difference. The only thing is that when it comes to a color image, the three components has to be considered separately and the operations has to be done separately, and finally it is merged into a single result. We have already discussed at the very beginning of the CNN that each hidden layer in a convolutional neural network is responsible for capturing different features of an image. For example, I may have a first hidden layer which capture the edges of my objects in the image, whereas the second hidden layer might capture the textures of the object in the image. The third hidden layer may capture say the size of the object in the image, and so on. Now suppose that my first hidden layer is associated with capturing the edges. Now we know that in an image I can have horizontal edges, I can have vertical edges, I can have edges in say 45 degree, or I can have edges at 70 degree, right? So in short, what I have is I can have edges at any angle. So that is where multiple filters comes into play. So one crucial idea for building a convolutional neural network is, what if we wanted to detect say an edge, but the edge with vertical edges, edges that are horizontal, edges that are inclined at any angle as well. So in those cases, we use multiple filters. So as you can see, I have a color image of size 6 cross 6 cross 3. And then as you can see, I have two filters. I have one filter here, I have my second filter here. That means I am capturing, say here, if I capture a horizontal edge with this particular filter, with the second filter I will be capturing the vertical edges. So we have already seen from this slide as how we can work with an RGB image. So the same thing happens here, but now you see it has to be done with the filter 1, which has a set of values, and also for the set of second filter, which has a different set of value. So this would give me one set of output, again another set of output, which is a 4 cross 4 image, and then what I do is I stack these two outputs together. So I have this 2, which comes as my dimension of the output, and the reason I got 2 here is that I have in this example 2 filters. Now suppose I have one more filter, suppose I also have a filter 3, then in that case this 2 will be 3. So I will have a 4 cross 4 cross 3 output. So this is about multiple filters, and it is again one crucial idea behind building a CNN. So if I have a RGB image, so my red, green and blue component, I have an RGB image of size say n cross NC, where NC is the number of channels, that is 3. Suppose that this is a 6 cross 6 cross 3 image, and I am convolving it with a filter of size F cross NC. That is, I will have the filter for convolving with the red component, the green component and my blue component. And suppose my filter size is 3. So I have 3 cross 3 cross number of channels, which is again 3. So in that case, my output image would be n minus f plus 1. this is under the assumption that there is no padding or zero padding and having a stride of 1. So it is n minus f plus 1 cross n minus f plus 1 cross my number of channels NC bar. So that would be 6 minus 3 plus 1 cross 6 minus 3 plus 1 cross NC bar, which is equal to 4 cross 4 cross NC bar. And the important thing to remember here is that this number of channels NC bar is equal to the number of filters. So in this case, I have used only one filter. Now suppose that I am also having another filter, one more filter. In that case, my output would be 4 cross 4 cross 2. So just understand that this 2 or this channel has nothing to do with the RGB channel, but it has to do with the number of filters, and it is equal to the number of filters that we use. Now suppose if I decide to have one more filter, then this NC bar will be equal to 3. So I have 4 cross 4 cross 3 as my output image. Now let us look at a simple use case. Suppose that you have 10 filters which are of size 3 cross 3 cross 3 in one layer of your CNN. In that case, how many parameters does this layer have? So we know that in a CNN, we treat the numbers present in our filters to be as the parameters, right? So I have a 3 cross 3 cross 3 filter. So a 3 cross 3 cross 3 filter. So it probably means that I am convolving this filter with a color image, right? So that's something we can automatically deduce. So if I have a 3 cross 3 cross 3 filter, then the number of parameters that my network should learn is 3 into 3 into 3, which is 27, plus a bias value, which is 28 parameters. Now suppose that I have 10 such filters. So I have 10 such filters. In that case, the number of parameters would be equal to 10 into 28, which is equal to 280 parameters. Or, in short, what I wanted to convey is that no matter how big your input image may be, so even if it is a 1000 cross 1000 image, or say a 5000 cross 5000 image, it has nothing to do with the number of parameters. So even if you have a 10 cross 10 image, or if you have a 5000 cross 5000 image, both the cases, the number of parameters will still remain the same, which is 280, provided you are having a 3 cross 3 cross 3 filter and the number of filters to be 10.